Hi, I'm EE432. Today I'm trying on a survey on 2D object detection. Here is the content. I will first discuss the introduction of the 2D object detection and the history. Also, I will discuss some related topics, including the instance segmentation and tracking. Thirdly, I will discuss the major tasks and challenges, including the object detection, the core task, and the real-time inference. Next, I will discuss the approaches in 4 categories. And finally, I will discuss some recent and future works about the open world object detection. The object detection aims to locate objects and determine their category within an image or a video. The output of an object detection usually contains a series of bounding boxes and their corresponding categories. On the figure 1 on the left side, there is an example of object detection, which contains 3 objects, a dog, a bicycle, and a car. On the right side, there is a history of the roadmap of object detection. Before the introduction of deep learning, most previous approaches are using the traditional methods. For example, some handcraft features, sliding windows, and very basic classifier to determine a pixel belongs to background or not, or object. And the earliest method is called the VGDET, and after that, some methods like POG and DPM. After the introduction of the deep learning, it's in 2012, the AlexNet is proposed, and many research began to use the deep convolutional neural network to extract features. And in this roadmap, we can roughly separate the deep learning-based approach into 4 categories. The first is the answer-free method, which is the most advanced method. And another one is the anchor-based, and there are 2 subcategories. One is the one-stage method, and another one is 2-stage. A typical approach of the 2-stage algorithm is the RCNN, and is also the first deep learning-based approach for object detection. Here is the related topics. First, let's come to the instance segmentation. The instance segmentation predicts bounding box, category, and pixel level mask at the same time. Generally, for most instance segmentation models, they already have an object detection head and a segmentation head. On the right side of figure 4, there is a class box prediction and another prediction head to predict pixel-wise classification results. And on the left side, there is a demonstration of the instance segmentation, with both the segmentation mask and the object detection bounding box with category. Another related work about the object detection is tracking. The object tracking aims to identify the location of objects and track their movement as they move across a sequence of frames, and usually used in video tracking. 2 classical object detection-based approaches are SORT, introduced in 2016. Another one is Deep SORT, introduced in 2017, which utilizes a deep neural network to produce the re-identification. And in the figure, there is an example of the human tracking. The different human is captured by different color of bounding box, and their movement can be tracked by the models. Now let's move on to the major tasks and challenges. The first task is the object detection, the core task that determines the location and category of an object. For the traditional approaches, some challenges may include robustness of the handcraft features. They're only suitable for limited scenarios. The second one is the accuracy of classifiers, such as SVM and AdaBoost. They only have limited accuracy. And the second is the deep learning-based approaches. One of the research area is object occlusion, and it's shown in figure 6 on the right side. Another one is small objects in figure 7, usually applied in the remote sensing. And for the real-time inference is also essential for autonomous driving. As for the traditional approaches, the sliding windows is very time consuming. And for deep learning-based approaches, the efficiency of feature extractor result the reduce of the inference time. Now we'll discuss four approaches. As I mentioned previously, the object detection can be roughly divided into four categories. The first one is a traditional method. The Vilo-Jones algorithm is the most classical and typical approach, introduced in 2001. Another one is the Anchor-based two-stage method, which is a deep learning-based approach. Fast RCN is one of the typical approach, introduced in 2015, and some Anchor-based one-stage method, the YOLO series. YOLO 3 and YOLO 4 is the two best model of YOLO series, introduced separately in 2018 and 2020. Finally, we'll go through anchor-free method. The CenterNet we will discuss. Let's look at the first approach, Velo joins. So it is one classic traditional approach. We use the integral image to speed up the inference or detection. They also use a learning classification function, such as AdaBoost. By utilizing the cascade of classifiers, the inference time can be further improved. On the left side, there is the handcraft feature that is used in the VG algorithm. And here is a cascade classifier architecture. On the right side, there is an application in the object on the face detection. It has a very good result, around 2000. Let's look at a typical deep learning based approach, the fast RCNN. It had two stages. Generally, the stage 1 will do the region proposal. Usually they will use a selective search. And this part is also be the performance bottleneck. And in stage 2, the object detection stage, they will first do a feature extraction and mapping the proposed region to the feature map. And finally, to do the bounding box and class prediction. On the right side, there is a general pipeline for the fast RCN. Here is a YOLO series. As the most popular frameworks, the YOLO v1 is the first version of YOLO, which is introduced in 2016, and YOLO 9000 is the second version, introduced in 2007, and afterwards, YOLO v3 and v4 is proposed, which can be considered as the greatest improvement of YOLO series. Let's first look at YOLO v3. On the left side, there is a demonstration of the architecture of the output feature maps. For each cell of each feature map, it contains 3 bounding boxes and their corresponding information, such as the height, the width ratio, and the location, the coordinates. And also they provide class vectors, represent whether this object represented by this cell have a specific attribute or category. And on the right side, there is a general pipeline of the YOLO v3, which is a multi-scale network, contains 3 different resolution output of feature maps, which can detect different size of objects. Here is a more detailed demonstration of YOLO v3. The bounding box with dimension pairs and location prediction, which allow the mapping of non-constant positive predicted values to constant positive values. And also the k-means is used to generate 9 prior bounding boxes, so that the model only predicts the ratios, not the absolute height and width. And finally, the non-maximum suppression, the NMX, is applied to filter those generated bounding box and offer as a final results. On the right side, there is a graph demonstrating the inference time vs the MAP, the mean average precision on the MS Coco dataset, will highlight the YOLO v3's advancement. Now let's come to YOLO v4. In this presentation, we'll only focus on the mosaic augmentation that proposed by the YOLO v4 paper. The mosaic augmentation randomly combines 4 images and keep their bounding box correct, which can significantly enrich the diversity of the dataset. Finally, I will discuss the anchor-free method, the CenterNet, which is an end-to-end framework. Without the predefined anchor, and it also don't need to do the k-means to define the mean bounding box within the dataset. They define the ground truth within a Gaussian kernel to represent as a heat map. And it also replace a non-maximum suppression as a max pooling, because they can consider the center of the heat map with the highest value to be the center of the object. This approach can significantly improve the efficiency and with better performance in object detection. Now I will discuss some recent and future works. In this section, I will focus on open world object detection, and I will discuss 2 methods. The data clip, introduced in 2012, 2022, and another recent published work, YOLO World. Compared with the traditional object detection, the open world object detection is more in tune with human habits of perception of the world. Because when people are learning to classify or find objects, they can learn based on the vocabulary, not based on a limited class database. For example, the MS Coco dataset only contains 80 classes, and did not fit with the human perception of the world. In the figure 15, there is a general pipeline of the detect clip, which utilizes in the clip a contrastive language model pre-training, which have a very impressive zero-shot ability. And they are calculating the cosine similarity of the object and their text embedding. And then second approach is the open world object detection, the YOLO World, which is published in February 2024 on arXiv. By comparing with the previous approach, it have a better mean average precision. By leveraging the YOLO backbone network, the detection head, which have a 20 times speed up compared with the previous approach. On the left side, there is a general pipeline of this approach, which also have a simple pipe architecture. And here is the open world object detection, the demonstration of the results of YOLO World. You can see in this picture, it not only shown the categories exist in current dataset, the VOC or the MS Coco, they also include several different vocabulary not existing in the original dataset, demonstrate the impressive performance of their shot ability. I think in the future, the object detection will come to a new era, and the open world object detection will further be improved. And I hope one day those approach can be deployed in a cell phone with a lightweight architecture design. That's all. Thanks very much.